These are the notes on light. Isaac Newton had a hand in many areas of physics. One of the things he was really interested in, along with a lot of great physicists, was understanding light. Now, Isaac Newton speculated that light was made up of very, very small, fast-moving particles, which he called corpuscles. Now, that is a terrible name, and people kind of made fun of him. This is one of the things that Hooke and Newton came to blows about, not literally, figuratively. But it makes sense because, Isaac Newton, he's a pretty clever guy, and he noticed that the way light reflects is just like if you take a ball and bounce it off a wall. Very, very similar. So in some ways, you can actually still consider light to be a particle, and they call that particle a photon. The only problem with that is it doesn't explain all of the things that light does. So sometimes you have to show light as a wave. And in fact, usually we think of light as a wave, okay, because it is an electromagnetic wave, right? And this gets complicated if you get into quantum physics. There's what they call a duality, where sometimes you can prove that light's a particle and sometimes you can prove that it's a wave. But for the most part in these notes, we are going to stick with understanding it as a wave, because this is a unit on waves. But just keep in mind that depending on how you look at things and how you measure it, there is a certain way of proving that light is a particle. So it's a strange business. Quantum mechanics gets very tricky. So look at a reflection. Now that would happen if it was a particle, and that would happen if it were a wave, because it turns out waves reflect, right? So this is one thing that they both have in common. And remember, the angle of incidence relative to the normal is equal to the angle of reflection. Now, we like to think of light as being waves because, yeah, it has different wavelengths and different frequencies. So all the things that we've used about waves will apply to light. But light has a few things that also make it special. The speed that it travels is always the same. Well, this is really the speed of light in a vacuum. We use the letter C for celeritas, the lowercase c, celeritas, to represent the speed of light. Now, 3.0 times 10 to the 8th meters per second, not exactly that, it's like 2.99 something. Okay, but it rounds to that. The only problem is that is the speed of light in a vacuum. A vacuum, not a vacuum cleaner, a vacuum is emptiness, complete and utter emptiness, empty space. Now, it is almost impossible to get a perfect vacuum, but you can come pretty close, and especially if you're in outer space, it is extremely close to being a pure vacuum. The farther you are away from an atmosphere or a star, the more it'll be closer to being a true vacuum. So this is an incredibly fast speed, and this is actually the fastest speed. No object or energy can move faster than the speed of light, 3.0 times 10 to the 8th meters per second. We call this the speed limit of the universe, and lots of things come out of this. About 120 years ago, Max Planck, a great scientist, sort of like a mentor of Einstein, came up with a constant. Now they represent this constant with the letter h, lowercase h, and that seems strange because there's no h in Planck's constant, but it's just physicists like to use certain letters for constants. It's just a weird thing. And a lot of times it's like a k or an h. So there you go. H is Planck's constant. Now Planck's constant is 6.63 times 10 to the negative 34 joule seconds. Well, that is a very strange unit. That's a very strange number. Is that a really, really huge number? No, in fact, that is an incredibly tiny number. In fact, this number is super tiny. You could almost say that it is tinier than Avogadro's number is big. You know what I mean? In the other direction. Super tiny. But what does this represent? It's kind of like the digitization of the universe. On a big scale, everything looks smooth. If you make a ramp, it can look like a perfectly smooth ramp. But if you zoom in closer and closer, that ramp might look like it's made up of little steps. Like if you get too close to a TV screen and you see the pixels, right? Well, Planck's constant relates to the digitization of positions in an atom. So it's like the smallest distance, it relates to the smallest distance you can move, or a quantum. That's where quantum mechanics derives its name, that everything is made up of little units, okay? Not analog where you can smoothly transition anywhere you want, but little steps. Anyway, Planck's constant becomes very important when we're talking about energy and light. This is the equation for energy when it is contained in electromagnetic radiation or light. So E equals HF. Now F is sometimes represented by the Greek letter nu, but we've been using F for frequency, so we're going to just continue using that. Just keep in mind, sometimes there are other variables they will use in place of certain letters. So what this means is if you want to figure out how much energy light has, all you have to know is the frequency. And then you multiply it times that constant, Planck's constant, and boom. So the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. But the problem is that we usually talk about light not in terms of its frequency, but in terms of its wavelength. So if you want to relate energy to wavelength, well, that's a more complicated equation. Now we have to bring in Planck's constant and the speed of light. So notice that the energy contained in light is equal to Planck's constant times the speed of light in the numerator divided by lambda. You know what lambda means, right? For any wave, lambda is the wavelength, right? Think of it as the Greek L for the length, the wavelength, right? So, well, the numerator here is just a constant, so that's going to be the same for any kind of light, but the denominator will change depending on the wavelength of the light. So what this means is that the energy is inversely proportional to the wavelength. In other words, if you have a very long wavelength, that will have very low energy. If you have a very short wavelength, that will have a huge amount of energy. So remember that the energy contained in light is inversely related to the wavelength. So this is how you would do the calculation to calculate the energy contained in light. You would take two constants and multiply them together. Well, that's always going to give you the same product. Now, if we had more time, we would be doing a bunch of these calculations. We usually would do this in conjunction with calculating the energy of spectral lines, but we really didn't have time for that one. And then you divide it by the wavelength. Now, the wavelength is the thing that can change here. Depending on, let's say, the color of light, you would have a different wavelength. And again, the energy is inversely related to the wavelength. The longer wavelengths, lower energy. So when we look at the electromagnetic spectrum, which is all the different varieties or flavors of light that you can have, it runs a huge range from super, super short wavelengths to super, super long wavelengths. The shortest wavelengths are called the gamma rays. You don't want to be anywhere near gamma rays. It will not turn you into a Hulk or a She-Hulk or what else? Doc Samson. It won't turn you into Doc Samson. It'll just kill you in high enough dosages. Okay. Down the road from gamma rays, we have X-rays, which are still dangerous in high doses. We now use very tiny doses at the dentist or at the doctor's office. Very, very low dosages of X-rays, which are considered safe. Then we get ultraviolet radiation. All that stuff sounds kind of nasty. All that stuff on the left side. Now, those are the short wavelengths. Notice that it's 10 to the negative 16, 10 to the negative 14. Very, very short. And because of the inverse relationship, that means they have very, very high energy. Okay? They call a lot of those ionizing radiation, things that can strip electrons off of atoms. And then we get, after the ultraviolet, we get to the visible light. Now, ultraviolet means above violet, okay? And then violet is the most energetic form of visible light, okay? Then we run through the spectrum of colors we know, okay, winding up with red. Now, red light actually has the longest wavelength of any color that we can see, but that means it has the lowest energy. Red light, despite what people seem to guess based on gut instinct and intuition, red light has the least energy, okay? And then there's infrared, that means below red. Why is it called below? Because it has lower energy than red. It's actually longer wavelengths than red. Those are the colors we can't see. We are actually emitting infrared. If we could see infrared, we could walk around at night, no problem. We could walk around at night without any lights. It would be great. But we can't do that because the Earth actually also releases infrared radiation. After infrared, well, there's a bunch of other waves, including the radio waves. Radio waves are super long. Some of them are over a meter long, okay? So more than the length of your arm, and then they get much, much longer, super long radio waves. Well, those are harmless. Those are passing through you right now, all the time, bouncing around, traveling through the air. No big deal for radio waves, okay? And microwaves are also in that, near that range as well. And microwaves are only considered harmful when they are focused and concentrated like they are inside a microwave oven. Otherwise, they are generally considered harmless as well. So remember that the gamma rays have the short wavelengths. That's high energy, high frequency. Okay, because remember, frequency is directly related to energy. And then radio waves on the other end have the long waves. And in terms of visible light, the violet end of the spectrum has the higher energy and the shorter wavelengths. The red end of the spectrum has the longer waves. And if you ever want to remember this, just remember ultraviolet, like plus ultra, right, over the top, right? Ultraviolet is above, and infra means below, infrared. So that'll help you remember which end is which, I think. And there's the microwaves. On this one, it includes the microwaves, which you can see are between the infrared and the radio waves. So here's another one of these diagrams, but this one is flipped around. So notice the radio waves are now on the left, the gamma rays are on the right, okay? So this is reversed. And it also shows you which ones will penetrate the Earth's atmosphere. So obviously radio waves do, because we can receive radio signals all around the Earth, although they do bounce off different layers of the atmosphere, which helps us as well receive them. And notice that visible light, of course, penetrates the Earth's atmosphere because we get that light from the sun. How are we going to get that radiation if it doesn't travel through the atmosphere? But luckily for us, ultraviolet does not. X-rays, gamma rays do not. So we are not bombarded by all this radiation, which is traveling through outer space. That is one reason that astronauts, taikonauts, cosmonauts, vyomonauts, that's why they need to wear spacesuits. It's not just to protect against the cold vacuum of space and the lack of pressure. It's also to shield them from dangerous radiation, okay, that travels through space. The Earth's atmosphere is really a blanket that protects us in many, many ways. Okay, maybe not a blanket, that's not the best metaphor. A shield, I don't know, a shield and a blanket. And this diagram also shows you sort of the scale that the wavelengths are on. And notice that visible light is on the wavelength kind of like the size of a cell, okay? Now the frequency is listed here and also the temperature. Now this is in Kelvin, but obviously this is what we call black body radiation. So if you take an object and you take it to a certain temperature, well, it will release electromagnetic radiation. Cooler objects will release lower energy radiation, like radio waves. Like, in fact, the background temperature of the universe, which is only a few degrees Kelvin, like 3 degrees Kelvin, releases radio waves. That's what we call the cosmic background radiation. Now that's not very much, it's very hard to detect, and it's not going to bother us much. On the other hand, if you've got an incredibly hot star, especially if it's going supernova, well, you will get a lot of gamma rays. You'll get gamma ray bursts. Okay, that's at the other end of the spectrum, incredibly high temperatures. Interestingly, lightning bolts can generate gamma rays. A lot of people don't realize that things here on the planet Earth can actually generate small amounts of gamma rays. Okay, they had a satellite in space that was detecting gamma ray bursts, and then it realized, hey, some of these are coming from below me. Some of these are coming from the Earth. And then they noticed that it was concentrated where there were thunderstorms. So that's one of the most energetic things we get on the surface of the Earth. And by the way, there's lightning in the sun. Did you know that? Lightning in Jupiter, lightning in Saturn. People think lightning is just a terrestrial phenomenon, but it's actually way more common than you might expect. In fact, there's way more lightning, of course, in the sun or Jupiter than there is on the Earth. Interesting. So just keep in mind that these are all the different flavors of the electromagnetic spectrum, and I'm just referring to them all as light. Now, light technically is only the part that we can see, but they're really just all different varieties of the same thing. Now, are these pure energy? It depends on the way you look at it. You could think of electromagnetic radiation as being pure energy in its pure form, sort of detached from matter, okay? Not contained in the vibration of matter or in the motion of matter. Another way to look at it is it's a transfer of energy. It's energy going from one place and arriving somewhere else. So it gets into semantics and what you think energy is, but I like to think of the electromagnetic radiation as being the pure energy, detached from matter. It can be sent out through empty space. It does not need a medium to travel through. One way we can observe specific wavelengths of electromagnetic radiation is by exciting tubes of gas. If you excite a tube of hydrogen, well, then it will turn into plasma. The electrons inside the atoms will be jumping around in and out between the different energy levels, and that will release the signature spectral lines of hydrogen. Okay? The spectral lines, these ghostly lines, that's what it means, will show you that hydrogen is present. This is how we detect hydrogen in materials, even in distant stars and galaxies. This is how we really know what the universe is made of, as we mentioned back in the cosmology unit. Now, hydrogen releases these lines. Notice the really strong red one, okay, and the really strong aqua blue one. Helium, on the other hand, releases different wavelengths. Well, helium also has a red line, but it's in a different position, but it also has a very bright yellow line that hydrogen does not have. So when you look at a bulb of helium, okay, the overriding color is sort of that bright yellow one there, right? And the other colors affect it slightly, they blend. Most of the time when we see electromagnetic radiation, we're getting multiple wavelengths combined, which produces a lot of the colors that we are used to seeing, okay? But it is possible to produce a pure wavelength under certain circumstances. There can be different kinds of sources of light. Think of the difference between sunlight and moonlight. Okay, well, obviously the sun is much brighter. That's why the daytime is much brighter. And the moon is associated with the nighttime, but you might not realize the moon is out just as much during the day as it is at night. It's equally out during the day as it is during the night. The only phase of the moon that is only out at night is the full moon, by the way. But you ever see those weather reports where they show the nighttime weather report, and it's always like some kind of crescent moon or something, which doesn't make much sense because the crescent moon is going to be close to the sun. It's either going to set right after sunset or rise just before sunrise. So it really is not a good symbol of the night. They should just use stars as a symbol of the night, even though actually stars are in the sky during the day. Think about it. Right now, if it's during the daytime, there's stars up there. You just can't see them. The sky just gets too bright with all that scattered light from the sun. So obviously the sun is way brighter, and the sun is a luminous source, meaning that it is emitting the light. It is generating the light through black body radiation, okay? The moon, on the other hand, is just reflecting some of the light that falls on it. The moon, by the way, is not reflecting all of the light that falls on it. The moon actually has a relatively low reflectivity, okay, or what they call albedo. The Earth has a much greater albedo, especially the ocean, okay, especially clouds and the ocean. They reflect a lot more light than the moon. So imagine if you were on the moon looking back at the Earth, it would be dazzling, okay? You would need, Earth glasses, I guess, to shield yourself from the brightness of our planet. That's a new one. The moon, they say, has an albedo very similar to asphalt. So if you go out and look at a road, don't stand in the road, but look over at how bright that is, that's comparable to the average surface on the moon. Some areas are a little brighter, the highlands. Some areas are a little darker, the Maria of the moon. But in general, it averages out to about the reflectivity of an asphalt road. Okay. So there's a huge difference between sources of light. Okay. Some of them can be emitters of light. Others can just be reflecting it. Then, different media are what the light travels through. Remember, media is the plural of medium. So you can have a medium like air, or a medium like glass, or a medium like water. But if we're talking about them all together, air, glass, water, those are media. Get it? So some media transmit the light, they're transparent, like glass, air. Okay, you can see the object on the other side. Now this might surprise you when you think about there's something in the way, but I'm able to see through it, that unless you think about chemistry and that most matter is actually empty space. So it should not be surprising that we can see through glass, okay, or see through air, because most matter is empty space. Even the densest material is still mostly empty space, unless you get to like a neutron star, but we don't usually see those. Then you've got material that transmits the light, but you can't really see through it, like a translucent object. Like, look at that lampshade there. The lampshade, you can see the light coming through it, but you can't see the bulb, can you? Okay. And then we have opaque objects. Opaque objects don't let the light travel through it. They just reflect some of the light. So it depends on which part of the light they reflect that determines their color and their appearance. Okay. Obviously, something like a mirror would be opaque, but it reflects virtually all the light that falls on it. Other objects, like a dark-colored rock, are absorbing some of the light and reflecting others. Okay, so there's absorption going on and there's reflection going on. And then, of course, the color of an object depends on which light it reflects. So if you have a white source of light, like the sun, all the different wavelengths are mixed in there. That's what appears white to us. And then it falls on a surface. If that absorbs all those different wavelengths, well, then it appears to be black, like a black surface. If, on the other hand, it reflects much of the light, or many different wavelengths, then it appears white to us. Okay, obviously, if it reflects all of them, well, then it looks like a mirror, right? But if it reflects much of it in the different wavelengths, then it appears to be a white surface. That's the reason why in the summer, when it's bright and sunny out, if you're wearing a black t-shirt, you'll feel a little hotter than if you're wearing a white t-shirt, because you're actually absorbing more of the radiation than you're reflecting. Okay, and that's why generally dark-colored surfaces will get hotter as well in the sun. Now, if an object appears red, that means it's reflecting the red light, or it can actually be a combination of several wavelengths that combine to make the color that we see. So this is a very simple example, but a red surface is absorbing the other colors and reflecting the red. But sometimes it's a combination of wavelengths that make the colors we see with our eye. So if you have a light source like a light bulb, it is sending out electromagnetic radiation in every direction. That is called its luminous flux. Okay? And because it's spreading out in every direction, the farther away you get, the more spread out the light is. You can think about this if you think about a sphere surrounding the light bulb. Okay, let's talk about a sphere here with a radius of 1 meter. Well, obviously there's a certain amount of light that is reaching that particular sphere. Okay. Now, the formula for the area of a sphere is 4 pi r squared. You might be familiar with that formula. What about if there's a sphere a greater distance away? How much light would travel if you were 2 meters away? Well, it would be the same formula for the area of the sphere, but now the radius would be 2 meters, and remember it's r squared. So it turns out the light is now distributed over an area that is much, much greater. Not just twice as great, but 4 times as great. So the illumination, or the illuminance, of each of these spheres is getting less and less as you move away. You know this. If you want to have a bright light, if you want to read something, you might have to get closer to the light source. And the farther away you get, the dimmer it gets, of course. But what you might not realize is that it drops off with the square of the distance. It's an inverse square law. Just like, remember, gravity? Gravitational attraction drops off with the square of the distance. Well, here is another one. Illumination, or illuminance, drops off with the square of the distance. So if you were twice as far, okay, because it's 4 pi r squared, then it is 1/4 as much illumination. If you are 3 times farther, well, then it is 1/9. If you are 5 times farther, it's 1/25. Get it? Or 10 times farther, it's 1/100th, or 1% as much. So illumination drops off really rapidly. So think about how bright the sun is from the Earth, right? And consider that we are 150 million kilometers away from the sun, 93 million miles. Imagine how bright the sun would be if you were close to it. It's ridiculous. Remember, that light has been dropping off with the square of the distance very rapidly. So if we had more time, we would be doing these calculations, but just so you can sort of see how it goes, the source of light has a certain amount of luminous flux, which is measured in lumens. Okay, so in this case, 1,750 lumens. And then you have to divide that by the area of the sphere to determine the illuminance, or the illumination of that surface. How much is it lighting up each square meter? And then the unit of that is lux. So at the bottom you see 139 lx, lux. Now a lot of physicists pronounce this lux. It's Lux, it's the Latin word for light. And there's also another unit that they sometimes use called candles. So you can see where these come from. But I just can't say lux because I studied Latin, and the proper way to pronounce it is lux. So I'm stuck with that. Anyway, just so we would have normally, under normal circumstances, if we had another day or two, we would have done some of these illumination calculations, but just wanted you to sort of see how they go. Another interesting thing about light is what we call diffraction. Now, this is one of the ways that you can prove that light is a wave. Sorry, Newton. So, what they do for diffraction is they let the light travel through a very, very tiny opening onto a screen. Now, in order for this to work, the opening has to be very, very small. So I'm showing it sort of exaggerated here. And of course, any light source has a certain width to it. So notice that the rays from that source, these are the ray lines, travel onto the screen. And if you're beyond the edge of that, well, the screen would just be dark. Let's say there's no other light sources. So clearly the most light is falling right in the middle, just like you'd expect, right? And then a little bit of light is falling off to the sides where part of the object is being obscured because the slit is only so big, right? Now this is completely intuitive. This is exactly what you would have guessed. But what you would probably guess when there are two light sources, that they would actually sort of combine with each other because there's more light, right? So if you shine twice as much light through the slits, then shouldn't the brightest part be where they're sort of overlapping, where the light from one source and from the other source are combining? And then it should taper off on either side. This is also intuitive, But unfortunately, this is not what happens. Surprisingly, something completely different happens. What we wind up getting is a pattern, an interference pattern, where some areas, yes, in the very middle between them, yes, it is very bright, but then just next to that, you find an area of almost complete darkness. And then you find other bands getting successively dimmer as you move away from that position. So why does this happen? Well, remember, waves will combine with each other. They will interfere with each other. So the peaks of waves, okay, the crests will combine, and the troughs of waves will combine. Well, that's what we're seeing here. But also, don't forget that the crest of one wave and the trough of another wave can completely cancel each other out. So that is also what we are seeing here. We are seeing light waves combining and canceling each other in a pattern called an interference pattern. So the interference pattern is very cool, very interesting, and it pretty much shows you that light must be a wave, at least in this sense, because particles just don't do that. Particles don't interfere with each other, like two particles don't cancel each other out, right? See what I mean? But waves will do that. So this is one of the ways that they have shown that light is a wave. So to understand what's happening here, this diagram is showing the light as it is coming through the two slits. If you consider the slit itself as the source of the light, because it kind of acts like that from that point on, it might as well be the very source of the light. So notice that it's a circle around the slit, right? Now, the solid lines represent the wave crests, and the dotted lines, the dashed lines, represent the troughs, right? So wherever the solid lines meet up, you get that light band where the positive interference is occurring. Okay? The crest of one wave and the crest of another are combining to make it extra tall. And wherever you get the dark wave lines, that is when the crest of one wave and the trough of another are neutralizing each other. Okay? So it depends on the distance you are away, and it depends on the separation of the slits that determines the spacing, of the different interference patterns. So these diffraction patterns or interference patterns are caused by both positive and negative interference of light waves, and this kind of behavior can only be produced by waves. Okay, so it's one of the cool things that light waves will do. Here we can see what happens if you adjust the width of the slits, how far they are apart, and you can see that that will change the interference pattern at various distances. You can see all the wave crests where they combine and where they do not. Pretty cool. Really interesting property of light waves. Another cool thing that light will do is light can become polarized. So polarization is when all the light waves sort of line up with each other in one direction, let's say either up and down or side to side. Because actually when light is emitted by most sources, it's coming out in every which direction. Some of the waves, imagine, are going up and down, like let's say waves on the ocean. Some are going like side to side, and some are going diagonal, and everything in between. And that's usually the case unless the light has been polarized. So polarization happens when there's a few ways to do it. One way to do it is only allow the waves through that are going in one of those directions. So if you have very, very narrow slits that only let the light through that is going, let's say, up and down, well, then all the light that's going side to side won't fit through the slit, and it will get sort of blocked by that. It'll get reflected by that or absorbed. So polarization, like polarized sunglasses, only let in the light that is coming in one of the directions. And in fact, if the light is close to that direction, then some of it will come through. So if it only really completely blocks the light that is perpendicular, let's say if your bands are up and down, if your slits are up and down, then it will only really truly completely block the light that is going side to side, okay, perpendicular to it. And then there's a really cool thing about polarization, that if you have two polarized filters, one that is blocking the up and down and one that is blocking the side to side, and put them on top of each other, well, they will block out all the light. And then depending on the angle between them, okay, that will determine the percentage of light that comes through. So there's all kinds of neat applications of polarized filters. They're kind of a fun thing to play around with. Another way that light can be polarized is by reflecting off of a surface. So if the light rays are coming in all different directions and then they bounce off the surface, only the waves that are somewhat perpendicular, and let's say the way they're oscillating, to the surface are reflected. So other waves are not, okay? So that's one reason that people wear polarized sunglasses, because if you have it oriented the right way, it can block most reflections, which is usually one of the things that dazzles the eyes. Reflections of the sun, for example, off of another car can sort of temporarily dazzle your eyes. So that's one reason that we wear polarized sunglasses. Interesting, right? And you can make use of this with a camera filter. So if you have a polarized camera filter, and if you don't want to see the reflection, you could rotate the polarized filter one way. If you do want to see the reflection, you could rotate it another way. One of the neat things about polarized filters is that you can filter out different amounts of the light. So if you see the lady on the left here, she has two polarized filters, but they are lined up with each other. They're both polarized in the same direction. So that is letting in a little bit, about half the light is going through there, okay? If you rotate one of the filters, though, 90 degrees perpendicular, well, now that one is also blocking half the light, but it's the other half. So it's blocking exactly the same light which was traveling through the first filter. So there's a neat thing about polarized filters. If you hold them perpendicular to each other, they block out all the light. And then if you vary the angle, you will get a certain percentage in between them. So this is a way to vary the amount of light that is transmitted through a material, is by rotating the axis of polarity. Pretty cool, right?
Dun, dun, dun. So here we have a laser. Now, not this kind of laser, although I guess maybe it could destroy a planet. Okay, this is a green laser. Well, what does laser stand for? Light amplification by the stimulated emission of radiation. It's an acronym. So this is just a particular wavelength of light. Okay, I can hold it in my hand. So not too dangerous, not blowing away Aldrin, okay? But because it is light, we can easily observe things like diffraction. Here I have a diffraction grating. I have two different ones actually. And these have microscopic lines in them. You can't really see them, but if I hold it in front of the laser like so, you can see the positive interference. It's easier to see it if I move it. Notice how the spacing depends on the distance, okay? You can see the interference pattern that is occurring because this laser is just one specific wavelength. Here's another one I have with a different spacing. This one has 500 lines per millimeter. Okay, this one has 1,000 lines per millimeter. And you can see the difference because of the line spacing. And then what happens if we put two of them together? Let's see, two of them together. Isn't that neat? What about if I turn them sideways? You get a really cool pattern, right? So you get like you get an interference pattern in all directions. So remember, this is where it's positively interfering, and then they're getting fainter and fainter, and eventually you just can't see them anymore. Let's draw it in closer. Isn't that neat? So that's an interference pattern, and it's a lot easier to see this one than with light that has multiple wavelengths. And that was two with the, let's try this one now. Let's try this combination. Maybe this will look cool. These ones, they match up. Okay, these ones match up. There we go, similar. Okay, so you can see the interference pattern occurring with a very specific wavelength, and this would be green light. Okay, so, and here's the little diffraction glasses, which have a similar effect. These are the ones we sometimes use for the Spectral Lines lab to see the wavelengths split up. Okay. Another thing that will happen with lasers is polarization, but you don't see much difference. Here's a polarized filter, and you can sort of see, depending on the direction I bend it, which way the laser is oriented. Most of the laser seems to be oriented this way, and less of it is this way. Okay? So what if I take another polarized filter and put it in front of the laser? Well, with the same orientation, it shouldn't make any difference, right? It should do the same thing. Okay? So one filter and two filters act pretty much the same, but if I rotate one of my filters perpendicular, well, that should block out the light. Even though it's not perfect, there's a very faint amount coming through there, but it's essentially blocking out the light from the laser. Okay? So remember, two polarized filters. Let me turn the lights on. You can see this better. One polarized filter, okay, looks this way. If I put the other one on top of it to line up with that, okay, fine, no problem. But notice what happens as I rotate it, how it darkens. And it should be getting almost completely black now, okay, because one of them is polarized this way, the other one is polarized that way. So about half the light will make it through one filter, and the other half of the light will make it through the other. But when they're perpendicular to each other, okay, they block out all the light. Okay. But then there's a weird thing that happens when you have a third polarized filter. Well, you think, well, this one is blocking out, is only letting the light through this way. This one is only letting the light through that way. So it should block out all the light, right? But what happens if I take a third polarized filter and I insert it in between at a 45-degree angle? Watch what happens. Okay, I don't know if you can see that very clearly, but isn't that weird? Isn't that a weird effect? Now this one is hard to explain. You'll have to watch a separate video to understand why that happens. So notice it happens not at every angle. It doesn't happen equally at every angle. So that's the interesting thing about polarized filters, and we can use them to block out reflections, because reflections off a surface often have a single polarity, so it's easy to sort of filter them out. Reflections off a surface, I don't know if you can see the reflected light on the surface going dim depending on the angle I hold it. And here's one that has 300 lines per millimeter. Let's see what this one does. Oh yeah, so you can see if it has there must be a defect right there, huh? Okay, if it's 300 lines, that makes a really nice pattern. Ooh, that's the best one. Okay, really cool. I wonder if I combined this one with the 500 one, what I would get. What about that? Ooh, and then what if I put the 1000 one on top of that? Oh, craziness, right? And if I do them at all different angles, what about this? What about this? Ooh. Okay, so this is getting complicated. This is a whole combination of interference patterns overlaid with each other, but it's pretty neat. You can do cool stuff with this. Okay.
Another thing that can be observed with light waves is the Doppler effect. Now, we talked about this in the cosmology unit, and Doppler effect is much more noticeable when you talk about sound waves. It's kind of obvious, the high pitch of an approaching motorcycle and the low pitch after it passes by you, like the effect. But with light waves, it actually affects the color. And this is how we know about the redshifts of galaxies and the expansion of the universe and the Big Bang. So remember that light waves are affected when the source of light is moving, or when you are moving relative to the source, either way. So let's say a source is moving toward you, well, the light is going to be shifted blue. If the source is moving away from you, like most things are in the universe, the light will be shifted red. And that's the little equation for calculating the new wavelength, the apparent wavelength that you will see. But just because light is shifted red doesn't mean it becomes red. For example, if the light began as violet, it might still be violet. It'll just be shifted in terms of its wavelength a little bit toward the red end. So just remember that a red shift doesn't necessarily turn light actually red, but it can shift it detectably if we measure the wavelengths. And remember, we know the signature wavelengths, let's say for hydrogen, so we know exactly how much they've been shifted from where they ought to be. So this is how important light is. It's the way that we even know about distant objects. It's the way that we can obviously see things and detect things. Very, very important. And of course, it can travel across the whole universe unless it gets obstructed by something, blocked by something, or absorbed by something, right? So redshifts, remember, are the way that we know how far away galaxies are from us, how fast they're moving away from us, how much the universe is expanding. It's all incredibly important. So light waves tell us a lot about the world we live in. So that is the end of the notes on light, our very last notes in this course. Thank you.